In these notes, we're going to take a look at a different system for describing the location of a point on a graph, and we're going to talk about how to take the coordinate and that other language, the polar coordinate language, and talk about how to convert it back to our standard x and y coordinate system. So in the traditional rectangular system, we're used to describing dots on a graph by saying how far is it horizontally and then how far is it vertically as two separate measurements to describe the location of this final position. Now we're going to talk about a system that uses an r and a theta value instead of an x and a y. So we're still trying to describe the exact location of a dot on a graph, but for this other system, we're going to start off by describing the angle on the unit circle that the dot is being drawn on. For example, if I set something at 30 degrees, I would know it's going something into the first quadrant along this diagonal line. If I said 90 degrees, I would know that it's going somewhere on this vertical line going straight up. 180 degrees would be straight to the left, etc. So the theta value represents what angle on the unit circle are we drawing a diagonal line at. The other value is the r value. This one is going to describe what length along that diagonal line you should be drawing the dot at. For example, if that r value was a 1, you'd be saying a length of 1 away. That could be 1 foot, 1 inch, whatever the unit is. 2 would be 2 lengths away. 3 would be 3 lengths away, etc. So the second value describes the angle of the diagonal line. The first number, r, describes how far down that line to draw your dot. Now usually for drawing polar coordinates, you're actually going to have circles embedded on the graph, and the circles will indicate the length of 1, 2, 3, 4, 5, etc. for the r values. So if it says r of 1, you would just go to the first circle, r of 2 would be the second circle, etc. Now I do have a comment here about a small complication on your polar coordinate system, and that's whenever you have a negative r value, so if it said -1, -2, -3, you actually need to take the angle that they've given you. For example, if they gave you 30 degrees for theta, and you would flip it around to the opposite side. You would flip it across the origin. So instead of being at 30 degrees, you could add or subtract 180 instead to say that it would be at 210 degrees. So whatever the angle is, 90 degrees, if you add 180, it would actually be going down at 270 for where you draw your dot. So just take your negative r values and then flip them to the opposite quadrant. Follow the diagonal line across to the opposite side of the unit circle instead, and then draw your dot along that line. Just as far as why we learned this system, it actually came up a lot dealing with anything that moves in a circular motion. For example, describing orbital trajectories, if you're talking about like satellites orbiting a planet. These were all easier to describe positions and locations by using this polar coordinate system instead of by using our traditional x and y value system. So here I'm going to quickly walk you through plotting 4 different polar coordinates on a graph. Now my graph doesn't have the angles very well labeled on here, so I'm just going to be approximating where pi over 3 is, 7 pi over 4, 45 degrees, etc. But it does show the circles I was talking about earlier. So anytime you have an r value of 1, you should have a dot somewhere along this first circle. Whenever your r value is 2, it should be somewhere along the second circle, etc. So first let's talk about the point P. I always start with the theta value, which in this case is pi over 3. So if I had my angle labeled on this, it would be a line going somewhere along this diagonal up and to the right. It should be a little bit taller than it is wider. So along this diagonal line is pi over 3. And then since the r value is 2, that means along that line, I'm going to draw a dot on the second circle. So that would be my point P. Okay, now for point Q, again, start with theta. 7 pi over 4, if you're looking at the unit circle, that would perfectly cut in half this fourth quadrant. So it should be a diagonal line going down to the right. And then as far as determining how far along that diagonal line to draw the dot, notice that my r value here is negative. So this is that tricky situation I was talking about. Usually my line should be going down and to the right, but we're going to flip it and imagine the diagonal line going in the opposite direction instead. So just flip it across the origin. So if I'm going diagonally up and to the left and then hit the first circle, since the value was a -1, that'll be the location for my point Q. These can also be in degree mode instead of radian mode. That's no problem. Now negative angles, don't forget that that means that instead of rotating counterclockwise, we're actually measuring the rotation clockwise. So -45 degrees is actually the same as the 7 pi over 4 angle I was just talking about, the one that's going diagonally down and to the right, and usually it would cut this fourth quadrant perfectly in half because we're going clockwise 45 degrees. This one has a positive R value though, so I'm not going to flip it to the opposite quadrant. I'm going to use that diagonal line going down and to the right, and I'm going to draw my dot on the third circle since this has an R value of 3. So that would be the coordinate R using this system. And then here's one last coordinate that has a negative R value. So start off by recognizing 60 degrees. That would be that same diagonal line I was doing here in radian mode. I said pi over 3 was the diagonal line going up and right. That's pretty tall. This one is also that same diagonal line, but because it's a negative number for R, I need to flip it into the opposite quadrant. So just imagine that same diagonal line passing all the way through the origin and go to the opposite side instead. And since this one has a value of 2, I'm going to draw that dot on the second circle in the opposite quadrant of 60 degrees. So that is my point S. So that was just 4 quick examples of plotting some polar coordinates on a graph instead of by using an X and a Y coordinate. In many situations, we'll want to convert our polar coordinates to the rectangular system, and vice versa. We'll do the other way around in the next video. But for this video, let's talk about how to take that R and theta value and change it into the rectangular coordinate system so that we can measure the horizontal and vertical movement instead of saying how far along the diagonal line and at what angle is the line being drawn. So the equations we need to know for doing this are that X is equal to R cosine of theta and Y is equal to R sine of theta. Basically, you'll just take the two values that you're given in the polar coordinate, the R and the theta value, and you'll just plug them into these two spots and then compute it. You should end up with something like 2 times cosine of 60 degrees or 3 times sine of pi over 2. That's a trig function you should be able to evaluate and then just multiply it by the R number, and that'll give you your X and Y coordinates to write it in this system instead, your ordered pair. So whenever you're asked to find the rectangular coordinates and you're given a point in polar form, first just make sure you recognize that the R value is the first number and the theta value is the second number, and then make sure you know the formula X equals R cosine of theta and Y equals R sine of theta. As long as you plug those two numbers in, all you'll have to do is a quick computation. You can either evaluate the cosine of pi over 2 using your calculator, or for angles that we're familiar with, you can usually just do this off of the unit circle or from memory instead. So for me, an easy number like pi over 2, I'd rather just compute that off of the unit circle. Cosine of pi over 2 is equal to 0. 2 times 0 is 0, so that's the X value. And then sine of pi over 2 is equal to 1. 2 times 1 is 2, so your Y coordinate is 2. Writing this in the standard rectangular coordinate system, that's the coordinate system you guys have been using for years. They're just giving it a more specific name now. Our answer is just 0, 2. So here I've set up a second quick example for you. Again, we have the polar coordinate given to us, -3, 360 degrees. You can always tell it's a polar coordinate instead of a rectangular coordinate if the second number is an angle. So if it has a degree symbol in there, for example, that's a giveaway. Usually when you have a pi in there, that's also a good indication that they've given you an angle in radian form. So whether it's degrees or radians doesn't matter. Our formula is X equals R cosine of theta and Y equals R sine of theta. Once you set up your two equations, just compute them using whatever method you prefer. Again, these are numbers that can be found on the unit circle, so I usually tend to prefer doing that because I find it faster than typing everything into the calculator. So if you follow along with this computation, cosine of 360 degrees is just equal to 1, and then I did -3 times 1 as a separate operation here. And then for the Y value, sine of 360 degrees is equal to 0, and -3 times 0 is 0. So our ordered pair in the rectangular system is X comma Y, so -3 comma 0 in this case. So in polar coordinate, if you drew a dot at -3 comma 360 degrees, you should find that it ends up in the exact same location as drawing the dot going to the left 3 and not going up or down at all in this case. So that's it for the notes on graphing polar coordinates and on how to convert from polar to rectangular. Thanks for watching and good luck with the assignment.